Okay, here's experiment number 2. We have the scale 1 and scale 2. Essentially pulling up, and the force of the earth and the force of the mass pulling down. Looking at this, we need to select our pivot point, which is I'm going to select at F1. Okay, so the distance between the earth and F1 is 0.4 meters. The distance between the mass and the pivot point is 0.65 meters. And then the distance between F1 and F2 is going to be 0.8 meters. Okay, now, since we know that this is in equilibrium, we can say that the torque exerted by the earth and the mass are both, in this case, clockwise, and F2 would be counterclockwise. Alright, now we're going to set up our net torque equation and our net force equation, because not only is it balanced and not rotating, but it's also not accelerating. So we can set up two equations to help us solve this problem. So all the torques are balanced, so my net torque equation will equal to 0. So if we look at the distance of F1 to the pivot point, it's 0, so it's going to be F1 times 0, or just 0, so I'm not going to include that in the equation. So then we'll have the force of the earth, which is 0.4 meters away from the pivot, plus the force of the mass, which in this case is 0.65 meters away from the pivot, subtracted from the torque of F2, which is 0.8 meters away from the pivot. All this is equal to 0. Okay, so the force of the earth would be 1 Newton exerted on this. So this would be 1 Newton times 0.4 meters plus 6.5 newtons times 0.65 meters. And then I'm going to bring this to the other side. I'll add it. So we end up having F2 times 0.8 on the other side of the equal sign, and that being positive. Alright, if I divide through and solve for F2, I get 5.78 newtons for the force exerted by 2. So now I'm going to look at the sum of the forces. It's equal to 0 because we have 2 forces up and 2 forces down. So in this case, up will be positive and down will be negative. Since we're looking at Newton's second law and we're looking at the non-acceleration of the center of mass, we just have to consider the up and down. We don't have to worry about the rotation here. So when you're looking at Newton's second law, you're looking at the linear motion. In this case, it does not have any. Alright, so let's solve for F1. I wrote out Newton's second law. Essentially all of these forces equal to 0, so when we solve for F1, we have F1 plus 5.78 newtons minus 1 minus 6.5, which would be negative 7.5 altogether. Alright, that equals 0, so F1, when we look at this, will equal, okay, all of this will equal 1.72 newtons. Alright, so this is why we use the sum of the torques and the sum of forces in conjunction with each other. It allows us to solve for F1 and F2, and if we look at what the object is doing, again, it's not rotating, which means the sum of the torques are equal to 0, and it's not accelerating, which means the sum of the forces are equal to 0. So we're going to do experiments 3 and 4 pretty much the same way by setting up an extended force diagram, setting up the sum of the forces equation and the sum of the torques equation, and you can use them in conjunction to solve for everything you need. And that's pretty much statics.